Let me start my talk. It is going to be different theory, which is considered to be something dirty, chaotic, and not deserving attention of theoretical physics, which is wrong, because some best minds like Feynman, Zager, Heisenberg, Landau, Kolmogorov seriously attempted to solve this problem. Unfortunately, Kolmogorov led the whole community to the ice wall in Warsaw, trying to climb that ice wall. What I'm suggesting here is the back door around that ice wall leading to the solution. And of course, that's a very ambitious statement. I hope that to some degree I will justify it, but you're welcome to criticize me. So here is the thing. The turbulence problem looks deceptively simple. You have to find the limit of the solution of the Navier-Stokes equations with viscosity going to 0 at fixed dissipation rate. So here is the Navier-Stokes equation. The way I prefer to write them, I put all the gradient terms. Is it? Oh, I see. There is this thing which is repeated. So the gradient terms are put into one term, which is gradient of enthalpy. And the rest is just conventional Navier-Stokes equation plus incompressibility. So in this limit, Navier-Stokes equation tends to the Euler equation. If you simply tend viscosity to 0, you get Euler equation. That's a well-known paradox. And the resolution is there is an anomaly, or something well-known in turbulence, which is called boundary layer, but not just boundary. Anywhere in the fluid, there could be singular regions of smaller dimension, like vortex sheets or vortex lines, where there is very large vorticity and very large velocity gradients, which could compensate small viscosity in front of this term. So limit of Navier-Stokes when viscosity goes to 0 is not Euler. It's something else, which, as we will argue, is very beautiful, universal, and solvable. These regions where there is large vorticity, they are randomly distributed in space. That's what we see in simulations and in experiments. And therefore, velocity and vorticity are not really well-defined variables. It's not like they have singularities somewhere. No, the singularities are randomly distributed in space, so it is stochastic variables. At any given point, it's fluctuating because singularity could come and pass, and every point, velocity exists, but vorticity, for example, which is curl of velocity, does not exist. Omega is curl of velocity. So Prof outlined the general approach to the turbulence problem. He suggested using this functional, which is generating functional, exponential of some source j, integrated over space times some source j times velocity, integrated over space. And this averaging here implies averaging over some initial data. In other words, we are not finding one solution of Navier-Stokes equation. We are finding the ensemble, the family of solutions. And we assume that in the same way as with Newton dynamics, the family of solutions of Newton dynamics cover the energy surface, which leads to Gibbs distribution. And we are going to find something similar for turbulence. And Prof suggested the way to do that. But unfortunately, what he suggested is quite symbolic and not tractable. And that led to some pessimism and complications and put turbulence to a very high status of unsolvable problems, which we think it's not true. So this functional generates correlation functions of velocity field and satisfied functional differential equation, which is called Hopf equation, Hopf functional equation. So time derivative of this z equals some operator applied to z. So it's linear equation, but it is linear at expense of going to very high dimensional space. And this operator h, evolution operator, depends both on source and functional derivatives. Now, what we would like to find is something like a degenerate fixed point. Gibbs distribution is the degenerate fixed point of the evolution of Newton dynamics. Trajectories cover the energy surface, and we assume, it's called ergodic hypothesis, that the energy surface is covered uniformly. So we want to find similar thing. And in terms of the Hopf functional, that means there should be fixed point. Now, fixed point would require absence of dissipation. And for that, you would need to introduce external forces, which I don't want to do, because what is called stochastic forces, which are added to Navier-Stokes equation, is not something innocent and symbolic like adding an infinitesimal magnetic field to the ferromagnet. It's something which really looks like a big spoon with which you stir the whole fluid. And it is implicitly assumed in that approach, with stochastic forces added to Navier-Stokes, that this randomness which you add more or less corresponds to internal randomness of turbulence and just provokes it. It's not true. The solution which we present has different kind of randomness, much smaller than the continuous random variables distributed in space. So what I'm trying to say is that adding stochastic forces Navier-Stokes pollutes the beautiful universal process of turbulence, and therefore we should be avoided. So what we're considering is decaying turbulence. So we stirred, we've added whatever forces we have, shook the turbulent vessel, and then at some point was stopped forcing and then let it decay. And with small viscosity, this decay will take a long time, and that process becomes universal. And in the end, we have what's called fixed trajectory. Fixed point is stationary solution of Hopf equation. What we'll find is equation which decays, but in a very universal way. In other words, it's fixed trajectory. It's universal trajectory going to zero. Because, of course, the fixed point is velocity equals zero. The fluid will stop because energy will dissipate. So we're talking about the degenerate fixed trajectory, slowly approaching to zero. Now, Hopf equation is in principle compatible with such trajectory, but it's too general and too complex to compute anything. Its complexity of the Hopf equation is equivalent to the non-Gaussian functional integral, like in quantum field theory or in conformal field theory. So that misplaces turbulent in the same category as critical phenomena in statistical physics. And we claim it's much simpler. So we introduce very specific version of the Hopf functional. The trick is that if we find not such a general functional, you could find a solvable equation. And let me explain how that happens. This degenerate version of Hopf functional is called loop average. It corresponds to the source which is concentrated around fixed loop in space, not moving, fixed loop in space, not moving with the flow. Loop C of theta, and you integrate over C of theta three-dimensional delta function of R minus C. In other words, this is source which is zero everywhere except on the loop. And it's a vector source. And when you multiply it by velocity and integrate over space, three-dimensional delta function disappears, and you will get something which is very well known, which is called circulation. You will get circulation of velocity over the loop C. So what we're studying is something similar to the Wilson loop in gauge field theory, except this is a billion field. Velocity field looks like a billion gauge field. There is no gauge invariance. I'm not claiming any kind of gauge invariance. I'm not playing, analogy games and poetic analogies. I'm talking about exact equivalence. So turbulence is not equivalent to any gauge theory. But the Wilson loop, or exponential of circulation with imaginary factor and some number gamma, that average is very similar to Wilson loop. And the technology which was developed for the gauge theories, namely technology of loop equations, can be applied to that theory. And it turns out that it is much simpler than gauge theories.
Can I ask a question?
What?
Why did you see the factor of I?
What is?
Why did you put a factor of I in the experiment?
I'm sorry, I don't hear well.
Put a factor of I, square root of -1.
Yes, I is square root of -1, like last 300 years.
I understand. Wasn't there in the Navier-Stokes?
Oh, why did they introduce that factor? Because without that factor, it does not exist. Let me explain why. I thank you for this question. Without this factor, it doesn't exist, because both experiments and the theory, which I'm not going to discuss here, claim that distribution of circulation only exponentially decays. So exponential of some real factor times turbulence does not exist. Unlike exponential of I something times turbulence, because in other words, Fourier, this is in fact, this exponential with factor I is a Fourier transform of probability. But Laplace transform does not exist except as analytic continuation. If the probability decreases exponentially, then Fourier still exists, because you have exponential decrease of probability times oscillating factor e to the I gamma, that exists. But if you have e to the plus I gamma, plus gamma, then either at positive or negative gamma, the integral would diverge.
Would you say it decays in time or in size?
At large gamma, probability distribution of gamma decreases as exponential of minus gamma, and that is too slow for Laplace transform to exist. However, Fourier transform exists. And the second reason why we do that is, unlike the Wilson loop in quantum field theory, time reversal is not a symmetry here. So there is no symmetry between gamma and minus gamma. That corresponds to time reversal. Time reversal corresponds to change of the sign of circulation, which means complex conjugation. So this Wilson loop, this loop average in gauge theory, in turbulence, is a complex number. It's complex number less than 1 by absolute value. But without imaginary unit, it would be simply not exist. It will not be bounded, and then you would not be able to see the time reversal. Okay. I'm sorry, I don't hear well. I have a hearing aid, but if you have a microphone or come closer, I could hear well. But anyway, I will answer questions gladly. So here is the closed functional equation which you could derive for the loop average. It was derived in '93, and I derived it by considering same methods which were used decade before that in gauge theory. And I was very happy because it's abelian theory, very simple thing. It's a linear functional equation, as you will see. So I was very happy. Then I found some complications, and for 30 years I couldn't solve that equation. But late this year, finally, I found solution. So here is the equation. If you differentiate this Wilson loop, you'll find that its derivative will involve only two terms of the Navier-Stokes equation. The term with the gradient will drop because you integrate over closed loop, and integral over closed loop of gradient equals 0. Therefore, we have only these two terms. So computations, which I'm going to skip, which could be found in my big paper, reduce these two terms to some operator containing functional derivative with respect to the loop. So both of these terms, gradient omega, curl omega, and v cross omega, both of these terms can be expressed as some operators, which we'll write shortly. But I don't want to give you the derivation. Applied to the exponential. And that is a very important thing. It's very similar to the Hopf. And here's a big difference. Hopf equation contained both source and functional derivative with respect to source. This equation only contains functional derivative with respect to our source. Our loop C is a source, effectively. So when you have the Hamiltonian, which depends on functional derivative with respect to coordinate and doesn't depend explicitly on the coordinate, you would think that it would be solved in momentum space, right? It's translation invariant. So in functional momentum space, if you go to functional Fourier with respect to the loop, you hope to solve it. And that is exactly what happens. So it's not some approximation or some miracle, numerical miracle constellation. It's a symmetry. It's a symmetry of the loop equation. So it does not depend on coordinate, and therefore you could solve it by means of the plane wave. It's plane wave in functional space. Plane wave in ordinary space is coordinate times momentum, exponential of coordinate times momentum. Now, in our case, coordinate is the loop. It has internal variable theta. So we have infinite dimensional space because we, instead of one point, we have our points in our space is loops. So loop is a point, and corresponding variable p, if you consider this integral p dc, it's like a phase space integral. It is parametric invariant. Now, parametric invariance is a very important property, which is exact symmetry of that equation, and we want to preserve it. So this function does not change when you make diffeomorphisms, transformations of theta, because you have integral dc, which explicitly is parametric invariant. So therefore, if you have such an ansatz and substitute it into that equation, you will see that loop equations will be solved if P satisfies the following dynamics. Time derivative of P should be that operator L, where functional derivative with respect to C is replaced to P prime. P prime, theta derivative of P, because when you find functional derivative of that with respect to C, you integrate by part and you get P prime. So this is nonlinear, but explicit, not functional equation. All functional derivatives disappeared. Time derivative of P equals some algebraic function of P, and here is what we get. So this is, again, no approximation, it's exactly what you get when you take that operator which you derive from Navier-Stokes and literally apply it to this ansatz. You will see that if P satisfies this equation, where delta P is discontinuity of P and P is mean value, principal value, mean value of value limit from above and below. So if we have this equation, which algebraically depends on P, on delta P, but does not depend on theta, because dependence of theta will break parametric invariance, which is a property of this loop equation. So we have very singular, but rather simple equation. There is no dependence on the unknown variable, and there is no dependence on time. So this equation surprisingly can be solved, and solution is very non-trivial. Let me go one step further. So this equation looks scary because the solution cannot be smooth function. And if you think about that, parametric invariance requires it's not smooth function. Any smooth function of theta would not be parametric invariant. So only the function which depends on theta only in a discontinuities. Discontinuity is something parametric invariant. When you make transformation of theta, the position of discontinuity may change, but discontinuity doesn't change. And that is the key to the solution. So we found analytic solution of that equation. First of all, it has very simple dependence of time. It's inversely proportional to square root of t plus t naught. T naught is an arbitrary variable. If you look at this equation, on the left side, you have time derivative of p, and on the right side, you have something which is a homogeneous functional of p. So this term scales as pq. This term also scales as pq. This term looks horrible, but it also scales as p squared times p, which is pq. In other words, the solution, which is proportional to 1 over square root of t, solves this equation. Not approximately, not asymptotically, but exactly. Because if its time derivative of p is homogeneous functional of p of the third degree, therefore solution has this shape, square root of t plus arbitrary constant. Now there is, of course, also arbitrary rotation, because equation is invariant with respect to global rotation in vector space. And f of theta is something which satisfies fixed point. And you could look at that equation and you know, try and guess using Mathematica, and finally find explicit solution. So here it is. F is a limit of the polygon. So f is a function of the curve theta. So we represent the curve as the limit of the polygon. We take some large number of points on a curve, theta, I mean, from 0 to pi on the curve, and then you represent p as sequence of values in these vertices, and discontinuity is difference between neighbors. So you replace discontinuities by finite difference, and then you tend the number of these points to infinity. So here is what is demanded by the equations. It's not arbitrary angle alpha k. They have to be related to some rational variable beta. Why rational? Because from the loop equations, we get recurrent equation that this alpha k plus 1 equals alpha k plus some Ising variable plus minus 1 times beta. And beta is arbitrary number. However, for the periodicity, because after some number of steps, you're supposed to come to the same point, it's periodic function on a circle. Therefore, this beta must be rational number. And that is something totally unexpected. That brings us to the number theory. Rational numbers are enumerated by so-called Euler-Tauschent. So this ensemble of all the solutions of this equation is parametrized by rational number p over q, by some variables plus minus 1, and some number r, which characterizes the periodicity. So all these parameters, omega, which is a global rotation matrix, n, p, q, r, and the sigmas are random. For arbitrary values of these parameters, this ansatz solves the equation. Now, philosophy is that you have to find the statistical ensemble. Because Hopf equation and loop equations are linear equations, any superposition is also a solution. So we have to find superposition which corresponds to translation invariant in physical space, rotation invariant, and would have reasonable physical properties. So the solution which we suggest is the simplest possible solution. You just take every representative on this ensemble with unit with equal weight. So you have well-defined discrete system with rational numbers, and you do like you do in quantum mechanics. You just sum over all states, counting each state with equal weight. And that is a solution, and we claim this solution has very interesting physical properties which match what we expect from turbulence. So it's not a toy model like one-dimensional Burger's equation, but it's exact stochastic solution. So this may be not the most general one, or maybe there is some ambiguity here, which is resolved by assumption that correct solution is equally weighted representative of every of these discrete solutions. But at least what is definite, which could be checked with mathematical notebooks I present, that this is a solution for arbitrary values. So the remarkable thing about this solution that this thermodynamics is calculable. One can compute, for example, the partition function of this statistical system. If you treat this as a statistical system, if you count number of states, mu is the chemical potential, which which is the potential corresponding to number of points, which we want to, number of points we want tend to infinity, and therefore we want to tend mu to 0 so that some would start diverging. And these weights are all calculable, combinatorial weights coming from the number of ways you could make n sigmas to add up to a given number. And phi of q is a famous thing called Euler quotient. That's the number of different fractions of a given denominator q. And it's expressed in terms of the prime decomposition of number q. And that's a remarkable thing because in the end, it will lead to certain quantum effects, which would be observable effects, which you could see even in the spectrum. So observable effects in the solution I'm presenting for decaying turbulence have to do with discrete numbers and, so to say, quantum effects. This analogy with quantum mechanics and loop space actually leads to quantum effects. So here is asymptotic computation of this function. It's related to, in this particular case, it's related to some singular function of mu. It decays, it decreases, it diverges, which is to be expected. And everything is calculable. You could also compute more interesting thing, which is entropy, which is average of square of vorticity. Now, vorticity is expressed in terms of this discontinuity of the momentum loop P, and if you do that, you will get this time-dependent factor. So vorticity, it's called entropy. Average square of vorticity decays is 1 over t squared. So if you multiply it by t squared, you will get some calculable number, which can be expressed in terms of what's called multi-torsions or Jordan torsions, which are generalization of the Euler torsions. And again, it's calculable. So time dependence, the time derivative of energy is proportional to viscosity divided by t plus t naught squared times some universal coefficient b, which is expressed in terms of zeta function of 3. And you see that when mu goes to 0 and viscosity goes to 0, we could have finite dissipation rate. We have this enhancement of the dissipation happening for small viscosity. That enhancement is our version of this, what's called anomalous dissipation. It is known for a long time that if you have the singular vorticity structures like vortex line considered by Burgers, then the the divergence of the vorticity tends to something like delta function in viscous in the Euler limit, but at finite viscosity there is a very small core. If you take square of vorticity, integrate, you will find that viscosity cancels. So there is a classical phenomenon known in the vortex dynamics, how you enhance the dissipation. You have viscosity times integral of omega squared. That's the definition of dissipation. Now, integral of omega squared diverges somewhere because in conventional approach with turbulent velocity, it diverges because of singular core where vorticity diverges. In our case, it's a dual picture. We are describing the fluctuations of velocity field in terms of dual system. If you understand, by the way, this point, that what do we mean by dual system? Let me give you several examples. One known duality is two-dimensional quantum gravity, can be also expressed as matrix models. So there's a system with totally different dynamical variables, but statistically they are equivalent. Correlation functions of the two-dimensional quantum gravity can be expressed in terms of certain matrix integrals or some dynamical triangulation. So there is already another example is ADS CFT. You have fluctuating vector field, which is conformal theory, and it's suddenly dual to gravity or string theory. So there are, in physics, it's well known. Another example, of course, is equivalence of Schrödinger equation and Heisenberg matrix dynamics. So there are two different languages which describe the same variable, the same system. And what I claim is that we have that dual description of turbulence. Note if I don't present velocity field, any formula for velocity field. What I present is something which allows me to compute correlation functions of vorticity. And that can be done in terms of this solution for Wilson loop. So my equivalent dual system is this fluctuating curve P of theta, which I describe by mean this Ising variables, etc. So I have the dual system, which is this, one-dimensional fractal curve in higher dimensional space, and that system is dual to the decaying turbulence in the sense that all correlations of vorticity in the decaying turbulence can be related to certain functions described by statistics of this fluctuating curve. And I'm computing other things, like, for example, the most interesting thing is energy spectrum of decaying turbulence, and other things. They're all calculable here. It's just a non-trivial exercise in number theory. For example, vorticity moments. Vorticity moments.
Can I ask a question? What for this anomalous dissipation, mu has to go to. Oh.
I'm sorry.
Oh, I'm sorry.
I dropped something. So what did you say?
For this anomalous dissipation, that the chemical potential has to go to zero in a very particular way as the viscosity goes to zero.
Yes, like square root of viscosity.
Why are they related in that way?
Well, because I compute the dissipation is proportional to viscosity and inversely proportional to the square of the. That's why.
That's kind of answer.
So
answer
I define turbulence as a limit of the Navier-Stokes system when viscosity goes to zero, but dissipation stays constant. I keep dissipation. I'm looking for a solution where dissipation stays constant, but when viscosity goes to zero.
Isn't somehow the surprise that at large Reynolds number, all fluid flows have that property? You don't have to tune the fluid to become turbulent in that sense. You just have to push the Reynolds number to be large.
Yes, that's right. Well, I am finding the universal solution. The solution which I found is some universal fixed point. I mean, and there is no ambiguity except for the parameter of mu.
Okay.
Okay, so here's another example. The moments of vorticity are also expressed in terms of zeta function, of ratio of zeta functions and gamma function. And again, it's calculable thing, and they proportional some negative powers of mu also. Now, here is another surprise. Our system is less than one-dimensional. You would think I reduced, dynamics of vorticity in 3 dimensions to one-dimensional Ising model. It's not Ising model. It's less than Ising model. It's periodic Markov process with just 2 integer variables. You see, the thing is that these equations for recurrent equations for between positions between these functions vectors f, which are solved, right? These equations describe what's called Markov process. The next step, you may imagine random walk around the circle, and next step doesn't depend on the whole history, just depend on the previous state. So if you consider 2 integer variables, n plus initially is number, so there is some number of spins sigma, say there is n plus positive ones and n minus negative ones. Then I want to generate them one after another. They're random variables. So for the first one, probability is equal to ratio of n plus to total number. Once you know the first one, the next probability will change because there is one less variable. So it's a random walk with 2 variables, n plus and n minus. And probability for n plus to go to n plus minus 1 is this. And likewise, complementary probability n minus will go. And sigma is not an independent variable. For this transition, sigma equals 1, and this sigma equals -1. So I can describe this sequence of sigma as a random process, which only involves two integer variables. And that's the way to simulate it. We use this Markov. That means that if you want to simulate the system on the computer, you don't need to have the memory proportional to n. Your memory is n to the 0. You only remember these two numbers, and you consider this Markov process. And that's what we did with my student, Max Bulatov. We took 10 to the 8, we could take 10 to the 12, whatever. It's just a matter of what it fits into the, integer numbers. We generated a very large number, n, because we don't have to store anything. So we did it in the GPU cluster. This random process fits very well the GPU architecture and parallelization, and all problem is to collect large statistics. And we collected 10 to the 8 random samples and found some interesting results, which I'm not going to present today because we're still analyzing them. But the point is that this is as good as exact solution. If you thought that turbulence is three-dimensional random system, now I reduce it to one-dimensional, and this Markov property reduces to zero dimension. You have a question?
Yes.
Yes,
So
if you speak to the microphone.
This
yes.
is very nice with n to the 0 memory. Did you also compare with simulating the system directly and see whether both answers would be
I
consistent?
think either I should get closer to you or you should get
Can do
closer
both.
to me.
So
Read your lips and I can hear you.
You could simulate it also with the standard way, right? So just using the standard equations. It's very computationally expensive.
Yes.
But does it give the same answer? Is it consistent with what you compare?
It should, but nobody, to my knowledge, really simulated decaying turbulence. What they do, they introduce this big dirty spoon, which is called stochastic random forces. And they hope they just make things better. In my view, they totally pollute the turbulence. So I now would insist that the people who simulated turbulence, Navier-Stokes, would actually do very simple thing. They take their dirty spoon, random forces, make very turbulent flow, and then they turn off their forces and see how it decays. And then they study statistics, which is going to happen in absence of this continuously distributed random forces, delta correlated with some wavelengths. We don't want that, because that's not what is there internally. And then I could compare it. So I have seen experiments where something like that was done, physical experiments. Experiments like when you insert vorticity from four corners of big water cube, and they make a blob in the middle, far from the boundaries. There's a turbulent blob. It's called confined turbulence. Then, indeed, there is no external forces. It will then decay by its own laws. And what the person who did it told me is that there are two regimes in decays. First, it decays by some slower power, and then it decays by some faster power. And that faster power probably means pollution from the boundaries. And the slower part of the decay is something which is internal process of the decaying turbulence. So decaying turbulence, in my view, should be revised because we have now very specific predictions, and these predictions don't apply to the forced Navier-Stokes equation. Because in my view, forced Navier-Stokes equation is polluted Navier-Stokes equation. So I'm almost done. I don't want to take too much of your time. I think here is the most important thing I want to tell before I draw my conclusions. The most important thing is the following. It is known that when you perturb certain nonlinear system near the fixed point, then small deviations from the fixed point decay exponentially with time, and the coefficient in exponential is called Lyapunov index, and that basically either it is a stable system, or it goes around in circle, or it's unstable. Now, in this case, we don't have fixed point. We have fixed trajectory, which decays in a very specific way. Turns out in this particular system, small deviations decay not by exponential, but a power law. And there is explicit equation for the spectrum of this anomalous dimension. And that's something which I really celebrated when I found, because how could we get scale invariance and spectrum of dimensions in a system when there is no scale invariance? You know, Navier-Stokes equation is not scale invariant. Whatever you try to make of it or fantasize about it, there is no renormalization group, there is no field theory, there is no conformal field theory. These are all fantasies. These are all blah, blah, blah. It is an equation without conformal symmetry, period. But this thing indeed has a scale invariant only in linear approximation. There is a scale, time dependence goes to some spectrum lambda, and there is some explicit spectral equation which I could write down. Unfortunately, I cannot solve it arbitrarily for arbitrary large n and go to the limit of n going to infinity. That would require much more effort, and I hope my friends in the number theory community will help me. They are already helping me, actually, helping me with other computations, because all this is one very well-defined exercise in number theory. It's a very well-defined ensemble, which I call Euler ensemble, of these sigmas, of these fractions P over Q. And statistics is a good exercise in number theory, which involves Euler torsions and generalized torsions, which are called multi-torsions. So let me draw my conclusions. So we have a solution for a loop average in decaying turbulence, and that shows non-perturbative effects, which effects are missing in weak turbulence expansion. So typically what you could do, and that's what everybody does, this or that version or disguise, or preying on Kolmogorov or preying on the normalization group or Wilson, you iterate in nonlinear term in the Navier-Stokes equation, okay? If you consider very large viscosity, then you could neglect nonlinear term. You have laminar flow, small correction. It's called weak turbulence. You could get something like field theory. If you have random velocity or random forces, you have some kind of diagrams in field theory, and you get expansion in the parameter, which in fact is large. It's 1 over nu. Whatever you want to say, it's always expansion in Reynolds number, not in inverse Reynolds number. So what you really want to do is to solve it exactly, or find the limit of large Reynolds number. So what we found out is that if you solve this problem non-perturbatively, there are effects which are not visible in 1 over nu expansion, namely quantization, because this quantization follows from mathematical equivalence of the loop equation to the Schrödinger equation in loop space. So the statement is that statistics of the velocity field, which is generated by this loop average exponential circulation, this statistics, on the other hand, can be viewed as a wave function of Schrödinger equation in loop space. And that's the reason why we get all this quantization, because how do you get quantization in the quantum mechanics? You get some periodicity requirement, and that gives you solution in terms of integer numbers or rational numbers. So that's exactly what happens here, and you would never see it if you work this naive 1 over nu expansion. Also, if you do 1 over nu expansion, you will never see the fixed point, of course. Fixed point is something which does not depend on nu in a continuous way, which is a fixed point. So that is the most striking result which we obtained here. And this quantum statistical system, which corresponds to solution of Schrödinger equation in loop space, can be regarded as a dual to turbulent velocity field theory, in the same sense as quantum gravity is dual to gauge theory in ADS-CFT correspondence. Correlation functions coincide and dynamical variables are different. Even dimensions of space are different. Compared to other critical phenomena, this theory is quite simple. It's not a field theory, but a quantum statistical system isomorphic to periodic Markov process with two integer variables. Therefore, it can be solved with arbitrary accuracy on the computer. The spectrum of anomalous dimension presents a formidable mathematical problem in conformal bootstrap. Still, the spectral equation in this theory is explicitly calculated at any finite n. Only limit of n going to infinity I haven't yet done, but I'm sure that with help perhaps of my friends from number theory, it is doable also. So it becomes a continuous spectrum, this spectrum of dimensions. So it will become continuous spectrum in the limit of n going to infinity, and that would lead to modifications of power decay, and that would actually mean that there is no such thing as multifractal scaling laws. They're all modified by logarithm because continuous spectrum of dimensions means there are no scaling laws. Some non-trivial functions of logarithm. So a solution is conceptually simple but technically involved. It reveals unexpected relations between turbulence and number theory. So it's not difficult to check this solution. One could look into my mathematical notebook where I take this expression, substitute in the equation, everything cancels, and you get the solution. In particular, the anomalous energy dissipation constant is related to prime factorization of large integers. And there are other analogies and quantum effects which are quite unexpected in the continuum theory of turbulence. So analytic computation of decay spectrum remains a problem for number theory. We haven't solved it yet. So we need real and numerical experiments for decaying turbulence at extreme Reynolds number to verify the predictions of the theory. It has not been done because some very old and dirty, I would say, results for the decaying turbulence, in my view, they don't really, well, they are not at very large Reynolds number, and they are not careful about distinguishing random forces from internal randomness. So I would like to do something from first principles, from Navier-Stokes, without random forces. So this is basically summarizes my talk, and anybody are welcome to look into all details. There are 3 papers which I recommend. One is my old paper, which probably nobody needs to read now. It was 93 paper, published in 95. And another is recent physics reports. I wrote physics reports called Statistical Equilibrium in Circulating Fluid. That was this year in physics reports. And I did not present the solution, but I described in great detail the loop equations and all kinds of WKB approximation. You could solve these loop equations approximate to very large loop, and that leads to area laws. Oh, by the way, question whether that was confirmed. Yes, I forgot to say that. When I solved, it was before, a few years before, I solved the loop equations in the WKB approximation. When loop is large and area inside the loop is large, this Schrödinger equation, as usual, can be solved by WKB approximation, which leads to some nonlinear equation, and solution of the equation is arbitrary function of minimal area. So it turns out that a very specific prediction was made that distribution of circulation of large loops depends as some exponential of some power of circulation measured by some power of area. And that was confirmed with very high accuracy. I described that in this physics report. So this part is meshed. That was done in ordinary three-dimensional simulations and predictions of the loop equations, WKB solution of loop equations, were area law. Area law was confirmed, and recently there were more precise experiments. So that is an established fact that at least in the limit of large loops, loop equations correctly solved with turbulence. But now I'm trying to present the general solution, which doesn't assume that loop is large, which is an arbitrary function of the loop, and that has not yet been compared to experiment. So today's talk is described in the paper recently published in the journal called Fractal Frac, MDPI journal, and it's also available on arXiv. So to the theory or on the theory of decaying turbulence. So all the details can be found there. So that is all, and I'm ready to answer any questions. So please use microphone if you will ask questions.
You mentioned you presented solutions that showed scale invariance, but later you discussed the conformal bootstrap also. Was there also a conformal symmetry or just the scaling?
No, 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 and no.
Okay.
There is no conformal symmetry and no reason for conformal
Very
symmetry.
good.
And here is my simple answer to you. Vector field in conformal theory has standard dimension space -2. Okay, let's assume it's true for velocity, which has divergence 0, its conserved current has dimension d-2, but oops, vorticity also is divergent current. So vorticity should also have dimension d-2, but that's the kernel of velocity. Therefore, these two dimensions must be different by 1. Ergo, there is no conformal symmetry in turbulence.
Thank you.
I'll follow up maybe on Dio's question. You mentioned Kolmogorov's ice wall right at the beginning, and it was too slippery to climb. But do you reproduce, or maybe not in the decaying case, but in the homogeneous case, the Kolmogorov 41 scaling?
Yes, it's a good question because there is one exact result in Kolmogorov theory, namely that cubic correlation of velocity depends linearly on space. Other results are approximate or model. But this is exact identity. Unfortunately, if you take a curl, if you consider what is the consequence of this relation for velocity correlation for vorticity, you will not get anything because it's purely longitudinal. So Kolmogorov relations relate to the potential part of the velocity. Rotational part of velocity drops. And what I'm deriving here is closed equation for rotational part of velocity. Now, here's the physics of that. The difference, huge difference between potential part of velocity and rotational part of velocity is the following. Rotational part of velocity, which is vorticity, is distributed very sparsely in space. There are singular regions like, blobs or worms or whatever you call it, or Berger's vortex or sheets. They're all over the space, but they occupy smaller portion of the space. They're small, some fraction of space. So they're scattered like a gas of vortex blobs. Now, velocity is totally different. Velocity is given by Biot-Savart integral. And that Biot-Savart integral is integral of vorticity cross gradient of 1 over r, and that has a long tail. It's like dipole moment, right? So at any given point, velocity field is influenced by vorticity everywhere in space, which makes local velocity simply a Gaussian variable. The simplest statement you could say about velocity field, which is confirmed by experiment, is that local velocity is Gaussian variable. End of story. It doesn't describe all this beautiful picture of vorticities because it drops. So potential part of velocity indeed is a very simple thing. Unless you hit one of those sparse vorticity regions, you simply have Gaussian variable just by the law of large numbers. If you have large number of small contributions from all remote Biot-Savart contributions from other blobs, they add up and make a Gaussian variable. Central limit theorem applies here. The same applies to the strain. If you consider a symmetric part of the Hessian of velocity, you will get the same thing. You will get actually interesting thing. You will get three-dimensional traceless matrix, which is a Gaussian. And that leads to very specific predictions for this symmetric part of the Hessian. Because it's traceless. It's not just 3 by 3 symmetric matrix, it's traceless matrix, but you can compute all moments, and that is something simple. Now, if you consider moments of circulation, that's totally different story. Circulation is non-zero only if it encircles some vortex structure. So, say, for example, if you make a loop and that goes, so suppose there's a vortex ring and you go around that ring or something like that, or some other vortex structure actually is unavoidably interlinked with your loop. Then, and only then, you will get non-trivial circulation. So circulation, distribution of circulation is very different from distribution of velocity. So people don't make distinction between what's called moments of velocity. They consider difference of velocity. And that difference of velocity in neighboring points is related both to potential and rotational part. But if you separate this, you'll get different, two different laws. And for the vorticity part, I make certain prediction for loop equations, and they are satisfied by an experiment. And potential part, I don't know how to solve potential part. But the last thing I want to say about potential part, it may not exist. It may not be universal. Because if the correlation function grows with distance, like correlation at this point is proportional to r cubed, and it is related, the farther you probe velocity, the more it influences. That means the boundaries must influence. There is no proof that the dynamics of velocity field is totally universal, because a growing correlation is something totally well, I mean, that thing in field theory shouldn't exist. A growing correlation means there's no correlation. It's not correlation. It's influence of walls of the, truck going on a neighboring street. So I would think that only vorticity dynamics indeed is universal and calculable. Anybody could approach me. I'm going to be here till the end of the week. And if people have kind of, maybe I hypnotized you and now you will get off this, hypnosis and find the real question to me, you're welcome to find me here. I'm going to be here tomorrow, and tomorrow I'm leaving on Friday morning. So I will gladly answer any questions.
So does it